Bioscope, Visual Unfairness Diagnosis for Graph Embeddings, Data Science Honors, Data Analytics, IA2. Abstract. The issue of bias, that is systematic unfairness, in machine learning models has recently attracted the attention of both researchers and practitioners. For the graph mining community in particular, an important goal towards the algorithmic fairness is to detect and mitigate bias incorporated into graph embeddings, since they are commonly used in human-centered applications, for example, social media recommendations. However, simple analytical methods for detecting bias typically involve aggregate statistics, which do not reveal the sources of unfairness. Instead, visual methods can provide a holistic fairness characterization of graph embeddings and help uncover the causes of observed bias. Methodology. Bioscope lies at the intersection of vector embedding visualization and the analysis of fairness for graphs embeddings. Additionally, inspiration has been drawn from graph neural network visualization tools. This paper discusses the definitions and formalism adopted for graph embeddings. This formalism is then used to define the fairness and to provide the fairness notions. Graph embeddings. Graph embedding algorithms take a graph G equals V, comma E as input and present each node in RD, where D is a dimensionality parameter provided to the algorithm. The node level vector representations are chosen such that two nodes Vi and Vj are close to each other in G. Graph embedding algorithms can also be clustered into several methodological classes: matrix factorization, random walk, autoencoder, and GCNs. Recent work has also embedded nodes into hyperbolic space, which better represents hierarchical tree-like structures. Fairness notions. Recent work has evaluated the fairness graph embeddings and builds upon broader fairness definitions established in the algorithmic fairness community. Fairness definitions typically fall into two classes: individual and group. Individual fairness ensures that the algorithms treat two similar individuals similarly. In contrast, group fairness ensures that two subpopulations in aggregate are treated similarly. Individual fairness. For individual fairness, we build upon the definition of individual fairness for graph embeddings introduced in Inform, which assigns a non-negative unfairness score to each node, where n of u comma k is the k-hop neighborhood of u given by the nodes reachable from u in at most k steps. Group fairness. Regarding group fairness, the score is based on the definition of group fairness for graph embeddings proposed by Fairwalk. The motivation behind it is to promote recommendations in the context of a recommender system where all population groups are equally represented. Tasks. This research paper aims to answer the questions defined in the previous sections through the following tasks, as explained in the given table. Design of Bioscope. Visual encoding interactions implemented in Bioscope were selected by analyzing a series of independently drawn sketches that were created to satisfy the tasks mentioned previously. Task 1. For the degree of distribution, the bar chart idiom was selected, since it makes use of the most effective magnitude channel to encode ordered attributes according to the effectiveness ranking for visual channels presented. Task 2 was to achieve the comparison task by providing side-by-side views in the overview, whose main visual components are shown as follows. In particular, the same network is displayed on both sides of the figure using the spring layout, while the node colors depend on the fairness of the respective embedding algorithm. A sequential color scale is used since the attribute being encoded is quantitative. Darker colors are associated with higher unfairness scores due to the negative nature. Task 3. This is addressed using the diagnose view. This view lists the nodes together with their unfairness scores, allowing the user to select a focal node and uncover the causes of bias. Specifically, the main components of the view are an interactive table containing the node IDs along with their unfairness scores, the projected embeddings affecting the score of the focal node, and the corresponding subgraph topology. The user can sort the list of nodes based on their IDs or scores by clicking on the arrows next to the column names of the table. This tool described is shown in the following diagram. Results. Node attributes and the IDs and associated fairness scores are displayed on mouse hover. The context legend displayed in the diagnose view, top plot, conveys the scale of the distances observed in the scatter plot, bottom plot, where the embeddings that affect the score are plotted. Future scope. In the present design study, large benchmark networks were handled. Therefore, responsiveness issues had to be overcome. A simple heuristic was used to minimize the number of edges in the visualization by filtering out non-salient edges. In the future, exploration of more sophisticated heuristics as well as graph abstraction methods have been planned. There are plans to make certain additions in order for the tool to better support the needs of its target. These include the extension of the benchmark suite used with other networks popular within the graph mining community, as mentioned earlier. Motivated by the recent efforts made by the algorithmic fairness community, the Bioscope, an interactive web-based visualization tool supporting end-to-end visual unfairness diagnosis in the graph embedding algorithms, was built. Thank you.